Hello friends. Let's go back to 2014 when the renowned director Christopher Nolan released his blockbuster film, Interstellar. This movie took us on an epic space adventure, showcasing scientifically accurate concepts like wormholes, black holes, and alien planets. However, the most awe-inspiring moment came in the film's climax when the protagonist, Cooper, ventured into the black hole named Gargantua. As he plunged deeper into the darkness, he encountered mysterious grain-like particles that pelted his spacecraft, leaving behind scratches and causing it to catch fire. Forced to abandon his vessel, he continued his descent into the enigmatic black hole. To his astonishment, Cooper found himself in a surreal five-dimensional space where he could communicate with his past self through the power of gravity. These scenes may have left you wondering, could this be possible? Does such a phenomenon exist within a black hole? If we were to encounter a black hole firsthand, what would we observe? In today's video, let's delve into these intriguing questions and attempt to comprehend the extraordinary aspects of black holes. Not too long ago, around a century back, the concept of black holes was completely unknown to humanity. It was the brilliance of Einstein's theory of relativity that eventually led to the discovery of these mysterious cosmic entities. Einstein's theory can be divided into two parts: the special theory of relativity, published in 1905, and the general theory of relativity, formulated in 1915. The special theory of relativity elucidates how speed influences the passage of time. Imagine being aboard a spaceship hurtling through space at an incredibly high velocity. While on board, you wouldn't sense any change in time. It would seem as if time is flowing at its usual pace. However, observers on Earth would perceive time differently. The faster the spaceship travels, the slower time passes for its passengers compared to people on Earth. This fascinating phenomenon is known as kinematic time dilation. Einstein's general theory of relativity delves into the influence of gravity on time. Published in 1915, this theory reveals that even gravity can bend and warp time. The stronger the gravitational force you experience, the slower time will pass for you compared to someone in a weaker gravitational field. This captivating concept is referred to as gravitational time dilation. You can check out my video on time travel where I explored this concept more precisely. In the movie Interstellar, these ideas are depicted brilliantly. When Cooper and his team land on the Aqua planet, they encounter an extraordinary phenomenon. 1 hour on this planet is equivalent to a staggering 7 years on Earth. This time dilation occurs because the Aqua planet is situated close to the massive Gargantua black hole, and the immense gravitational force from the black hole significantly impacts the passage of time on the planet's surface. To help us grasp this concept, Einstein encouraged us to envision a space-time fabric resembling a mesh, upon which all celestial objects are situated. The mass of these objects causes the space-time fabric to bend. As this mesh bends, it not only exerts a stronger gravitational pull on physical objects, but also results in time dilation. Additionally, other forms of energy, such as sound, heat, and light, are influenced by this gravitational effect. Yes, you heard it right. This was another groundbreaking conclusion drawn by Einstein, that gravitation impacts nearly everything in the universe. It's not just physical objects that feel the force of gravity. Heat, sound, and even light is also affected. This revelation led to the possibility of the existence of celestial objects with an immensely high gravitational force, capable of completely absorbing light. Consequently, these objects would appear entirely black to us since not even light could escape from them. These mysterious entities, as you might have guessed, are what we now know as black holes. Interestingly, when Einstein presented his theory of general relativity, the idea of black holes was purely theoretical. Einstein acknowledged that gravitation influences light, making objects that absorb light a possibility in theory. However, during his lifetime, the concept of black holes seemed rather bizarre and abstract to him. Although theoretically plausible, he was skeptical about their actual existence. In fact, at the time of his passing, the term black holes had not even been coined yet. Here's an intriguing fun fact. A crucial aspect of Einstein's theory is that the speed of light sets the limit for the influence of gravity. Gravity's force doesn't propagate instantaneously everywhere. Its upper limit is the speed of light. To illustrate this, imagine the sudden disappearance of the sun. We wouldn't immediately sense its absence on Earth. Instead, we would come to know about it 8 minutes later because that's how long it takes for sunlight to travel from the sun to Earth. Astonishingly, according to Einstein's theory, the gravitational impact of the sun's disappearance would also be felt 8 minutes later. Following Einstein's groundbreaking work, other scientists worked on the theory of general relativity, tackling various equations and seeking solutions. Their theoretical efforts eventually provided evidence for the existence of entities like black holes. By the 1960s, it was widely agreed among researchers that, while theoretical, black holes were real possibilities existing in space. The term black hole first appeared in a magazine in 1964, but it gained significant popularity after physicist John Wheeler promoted it in 1967. Although the name black hole sounds dramatic, it can be a bit misleading. Contrary to what the name suggests, there's no actual hole in space. Black holes form from stars, so there's still material at their centers. Stars, including our sun, sustain continuous nuclear fusion reactions at their cores, generating heat and light. The outward force caused by this heat balances the inward force of gravity, maintaining the star's equilibrium throughout its life. However, these reactions rely on fuel, such as hydrogen or helium. Once the fuel is depleted, there won't be any forces pushing outward, and the gravitational force will no longer be balanced. Consequently, the star will collapse under its own gravity, leading to the formation of a black hole. Our sun, with an estimated life expectancy of around 10 billion years, will eventually reach the end of its life. What follows depends on the mass of the star, and to understand this, let's refer to the life cycle chart of a star. For stars with lower masses, such as small or average-sized stars, they transform into red giants. Later in their progression, they can become planetary nebulae or white dwarfs. However, if a star is massive, with a substantial amount of mass, when it depletes its fuel, it cools down and transforms into a red supergiant. Subsequently, the supergiant undergoes a dramatic explosion, becoming a supernova. After this cataclysmic event, only a tiny core remains. If the core is particularly small, it is classified as a neutron star. But if the core is larger than that, we call it a black hole. Essentially, when a massive star collapses due to its own gravitational force, its mass becomes highly concentrated, and it can transform into a black hole. It's astonishing how small the volume of this compressed star can become. For instance, if a star as big as our sun were to turn into a black hole, its diameter would shrink to a mere 50 kilometers. Imagine such an immense object being compressed to such a tiny size. However, there's an intriguing twist when it comes to our sun's fate. It has been proven by the Indian-American astrophysicist Subrahmanyan Chandrasekhar. He introduced the concept of the Chandrasekhar limit, which states that the maximum mass a white dwarf can have is 1.4 times the mass of our sun. Beyond this limit, a white dwarf cannot remain stable and will either become a neutron star or a black hole. Since our sun's mass is below this critical limit, it won't grow up to become a black hole. Instead, it will eventually transform into a white dwarf as it completes its cosmic journey. Now that we have explored the reasons for the existence of black holes, let's delve into the different types of black holes. There are primarily 3 to 4 types known to us. The first and most common type is the stellar black hole, which forms when massive stars exhaust their nuclear fuel and collapse under their own gravity. Within our Milky Way galaxy, scientists estimate that there may exist anywhere from 10 million to 1 billion of these black holes. Next, we have the primordial black holes. These black holes are only theoretical and hypothetical at this point. They are presumed to be as tiny as an atom but possess a mass comparable to that of a mountain. However, much remains unknown about them. The third category is the supermassive black hole. As the name suggests, these black holes are colossal, with masses surpassing that of 1 million suns combined. Despite their immense size, they are found within a compact space, with a diameter as large as our entire solar system. Scientists believe that at the core of most major galaxies, including our own Milky Way, there resides a supermassive black hole. The one at the heart of our galaxy is known as Sagittarius A, while the supermassive black hole depicted in the film Interstellar was named Gargantua. In addition to these known types, there is a possibility of a fourth type called the intermediate black hole. This type is believed to fall in size between stellar and supermassive black holes. However, no concrete evidence has been discovered to support their existence thus far. In the photo, the first notable feature is the orange-colored ring encircling the black hole, known as the accretion disk. This is a significant characteristic of black holes. Due to the immense gravitational pull of black holes, a vast amount of gaseous matter and debris is drawn toward them, remaining in a floating state all around. Similar to how planets revolve around the sun due to its gravitational force, the matter around a black hole orbits at an incredibly high speed. The intense speed and compression cause the matter to heat up significantly, transforming it into a fluid-like substance resembling fiery particles with temperatures exceeding 1,000,000 degrees Celsius. As the matter revolves at such high velocities, friction and compression make them glow, emitting electromagnetic radiation, predominantly in the form of X-rays. While the Interstellar movie accurately depicted the accretion disk, they portrayed it with an orange hue. In reality, our eyes cannot perceive X-rays as they lie outside the visible light spectrum. To facilitate representation, scientists typically use an orange-yellowish color. However, the actual color of the disk is closer to blue. In 2019, the first photo of a black hole was captured, and even then, the orange-yellowish color was used to represent the accretion disk. One interesting aspect that is more evident in the actual photo than in the movie is the brightness variation of the particles on different sides of the disk. This brightness asymmetry occurs due to the Doppler beaming effect. Particles spinning towards us appear brighter, while those spinning away from us seem dimmer. By observing the real photo, we can interpret the direction of the spinning particles by examining the brightness distribution in the image. Returning to the image from the movie, there's another captivating aspect to observe: the optical illusion created by the accretion disk due to gravity. When viewed from the front, it appears as though the disk covers the top and bottom of the black hole. This illusion arises because gravity has the power to bend light. The regions hidden behind the disk, when observed from the front, force light to curve around the disk due to this gravitational bending. However, when you view the black hole from the top, the disk looks like a regular round shape. This optical illusion is only noticeable when observing the black hole from its sides. Once you venture into the black hole, you will encounter the photon sphere, where the gravity is so potent that light begins to orbit the black hole. Since light is composed of photons, these photons start encircling the black hole. Consequently, if you were to reach this region of the black hole and survive, it would theoretically be possible to see the back of your own head, as the light forms a circular ring-like pattern. Beyond the photon sphere lies the boundary of the black hole, the event horizon. This boundary is significant because beyond this point, the gravitational force becomes so overwhelming that even light cannot escape. Consequently, everything beyond the event horizon appears pitch black. If you were to fall into a black hole and cross this event horizon, theoretically, there would be no chance of escaping. If light itself cannot break free, it is improbable for a human to do so. In the movie Interstellar, Cooper's spacecraft continues its descent into the black hole, crossing the event horizon, and then enters a fantastical five-dimensional space. However, it's essential to note that this aspect of the movie is purely imaginative speculation, since we remain unaware of what lies inside the event horizon. The creators of Interstellar went to great lengths to ensure scientific accuracy, even enlisting the expertise of a Nobel Prize-winning physicist, Kip Thorne. However, for aspects that remain undiscovered or unknown by science, the movie ventured into the realm of imagination. There is also a theory that suggests that a black hole is an opening of a wormhole, but what are wormholes? You can check out my video on wormholes to know more about them. Regarding the center of a black hole, Einstein's general theory of relativity offers insights. At this center lies what is known as the singularity, a region within the black hole where the curvature of space-time becomes infinite. Imagine the space-time fabric I mentioned earlier. Under the influence of a black hole's immense mass, this fabric bends so profoundly that it stretches infinitely. As per the theory of relativity, gravity affects time, energy, and everything else. With increasing gravitational force, time slows down infinitely. What implications does this have? If someone were to enter a black hole and somehow manage to emerge, would the outside universe have experienced an eternity in the interim? We do not know. Such concepts lead to intriguing theories, and I'd love to hear your thoughts on this in the comments below. A fascinating suggestion from one theory posits that inside the event horizon, light reflects off multiple points before reaching the singularity. This could potentially mean that inside the event horizon, objects might be visible despite our initial belief that we cannot see within a black hole from the outside. Until recently, our certainty about black holes was limited to a single photograph taken on April 10, 2019, by the Event Horizon Telescope. This groundbreaking image practically proved the existence of black holes almost a century after their theoretical validation. Falling into a black hole would be perilous. Due to the intense gravitational force, you would disintegrate within milliseconds. However, there is no need to fear black holes in general. Contrary to the misconception that they endlessly devour matter, black holes coexist within galaxy centers, playing a crucial role in stellar and planetary dynamics. Planets and stars in proximity to the black hole revolve around it, much like our solar system's planets orbit the sun. In conclusion, maintaining a proper distance from a black hole, akin to social distancing, will keep you safe and secure. While these enigmatic cosmic wonders remain objects of mystery, they continue to inspire awe and wonder as we explore the boundless marvels of the universe. I hope you found this episode informative. If you did, I kindly request you to like, subscribe, and share this video with your friends. I would love to hear your suggestions for future video topics in the comments section below. Thank you sincerely for your support. We will meet again very soon, but in the meantime, please feel free to explore my other videos. Goodbye.